Hi there. That's how a Peter Gabriel song started. I'll have to look up what song. Sledgehammer. Within the last month, I've had like 4 or 5 conversations about people trying that want to do some sort of cryptocurrency hardware project. And I don't think they've fully understood how cryptocurrency is slightly different than normal HSMs. And because this has come up so often, I want to talk about it here. So we're going to go to the purple board. Okay. Hi. Hello, purple board. I've missed you. All right. So the thing is, most people will overpay for a crappy product. And this crappy product is called a hardware security module. So, it's a crappy product because it's too expensive. The pricing's not transparent, and they make you pay a service fee. And then on top of that, it's difficult to use. But this crappy product has this claim that your key, will never, if you create a key inside this HSM, it'll never come out, which has not been the case. There's been active attacks on HSMs. They're crappy products. And they failed just like any other product, and the key has been exposed. But this is the claim they make, and due to the fact that they cost so much, a lot of time researchers don't have the ability to get hands-on, so they can't evaluate their claims. They send it to some lab, which that lab is in the business of giving out certifications, so I'm sure there's no bias there, just like there was no bias in the in the bond housing market giving out AAA ratings. Okay, sure, there's nothing to see here, but this is how these agencies work. And so this HSM is rated, according to this agency, that the key never leaves, and we believe them. Now, even if you do that, and even if you get the highest rating of protection and that basically just means you pay them a lot of money and then they give you a higher rating. And even if you get that rating, they'll claim that this key will never be exposed. And, there's even other certifications. There's FIPS, which is up to 3, and you can get level 4, which is like this amazing tamper. Oh, we can't see that. Well, this just says level 4. This tamper-proof thing, right? Imagine the super military kind of arrangement. And even if you get that, completely unsuitable for cryptocurrency. Let me tell you why. So this is like the traditional InfoSec world. They're like, well, if I have all this, then I'm good. And so you don't need anything, right? But the problem with cryptocurrency is you don't actually really ever need access to you never need the actual raw key. Like if the key is exposed, obviously that's bad, right? So bad. That's not the attack. That's not the attack. The attack is we just need to use the key. So if we're doing cryptocurrency, all we need to do is get the HSM to sign something. And it turns out HSMs are really, really bad at preventing like this kind of attack. They're really narrowly focused on just making sure the key doesn't leave, okay? They are really bad at preventing this kind of attack, and I'll explain in a second. So what do I mean by this? Well, we need to get the HSM to sign something. So imagine you have cryptocurrency and you get the private key and you put it in HSM. And in order to do a transaction, we just need, if we can get that transaction signed by the HSM, we can send it to the blockchain and then broadcast it and then move funds. So why am I saying this is like not, the HSM doesn't protect this? Because most HSMs will have some sort of PIN unlock, okay? They'll have this PIN unlock, okay? And this PIN unlock will be like a 4-digit PIN or something. And once the PIN is, use the PIN to unlock the HSM, it is basically completely open. There's very poor access control because they're trying to shoehorn everything into this thing called PKCS11, which is created by vendors so they can ship proprietary blobs. It's otherwise a horrible standard. It's a standard by C header. I mean, that's horrible, right? So everything about it is pretty bad, except that it makes HSM vendors happy because they can ship proprietary blobs. So this is what is still in use today, just showing you the lack of innovation in this area. And so what happens is that once the PIN is unlocked, you can just issue a sign. So now imagine you have a computer, and we're assuming the highest certified HSM device, the most expensive HSM device, okay? And you have this computer, and now this computer has malware on it, okay? And what this computer will do is what the malware will do is wait for you to enter your PIN and for you to authenticate to the HSM. And once that is done, it is going to then send the transaction without you knowing and have it signed and have it returned. Okay. That attack, it completely bypasses the threat model of the HSM. This HSM is now worthless. You've just overpaid. Again, it's congratulations. I'm sure your vendor loves you, but this is a piece of junk. Okay. It is not suitable for cryptocurrency. Likewise, when you're trying to build embedded systems that have cryptocurrency applications, you can't fall into the HSM trap. Okay, so let me talk about that. So it's not good enough so let's take my favorite, one of the favorite IoT secure element chips I like is the ATECC. Okay, and the ATECC 608. Okay, I'm sorry, despite the COVID, I thought this COVID vaccine would make me immune from all sickness. Turns out it's only making me immune from COVID-19. I'm a little sick today. Fraudulent claim. I thought it would give me superpowers. So this ATECC 608, all right, currently doesn't support the Bitcoin curve, okay? But let's just say it did. Let's say it was possible that this chip could actually support a cryptocurrency ECDSA signature, okay? So we'll just assume that's the case. Even if it was the case, you don't want to use this chip, okay? And I like this chip, but I'm telling you, don't use it for cryptocurrency. And the reason I'm saying don't use it for cryptocurrency is that because you cannot, even if this chip could hold a key, right, which it can't, a cryptocurrency key, you really don't want to use it for this because it would operate in the same pattern as the HSM, where you would have to unlock this thing, okay, and then once it's unlocked, it can sign. So this is otherwise known as a signing oracle. Okay, so meaning, and the actual ATECC itself, when used in the IoT purposes, is a kind of signing oracle, right? If in the traditional IoT sense, so why is a signing oracle okay? Arguably in the IoT sense and not cryptocurrency. In the traditional IoT sense, you have a microcontroller, and you have the 608 over here, and the whole point of this system is to authenticate to a cloud. And what the cloud really wants to know is, does this physical piece of hardware, does it have the key associated in that 608? And, there is ways to secure this link, which is typically over I2C. But a lot of times that's just left blank, where if you had physical access to the bus, you could sign something. But that sometimes is okay depending on your threat model, because what really is the cloud wants to know, and it's usually done through some sort of challenge response, that, hey, this chip is assigned to that hardware. So I'm just saying that the 608 is actually appropriately made for the IoT use case, and it is not appropriately made for the cryptocurrency use case because of this signing oracle problem. Now, there are products using the 608 for cryptocurrency applications, but they're actually really kind of twisting it into a way where it's being used to kind of just do the user authentication piece, and it's not really involved in any of the cryptocurrency pieces. So that is one way you could use it. It's really awkward to use in that sense, in my opinion. But it can work that way. Although I do think there's probably better chips if you're just trying to do that particularly PIN verification part. But the 608 can obviously do. Okay, so let's go back. So this is a problem with this signing oracle and cryptocurrency hardware, which is why you want to watch out for that. But as it turns out, we don't necessarily learn our lessons, because this has been talked about. So what do you need? All right. So what do you need to do cryptocurrency? Before I talk about this, you need to know, right? So the reason you need more than a signing oracle is that when the cryptocurrency transaction comes across, what you really want is for this magic piece of hardware to prevent the signing oracle. We are going to assume that this magic piece of hardware is somehow trusted. And what we really want is some sort of confirmation by the user to see that this magic piece of hardware is doing what it should be. So when the transaction comes over to send funds, right, we want the user needs to approve it. So we got to say yes or no. Okay. And how does the user do that? Well, so this transaction is coming over some sort of interface. It's going into this magic piece of hardware here, and most of the vendors have opted for some sort of visual feedback, so some sort of screen. And in that screen, it will show, approve transaction, right? So it'll show the transaction, and it'll ask to approve it. And then there'll be buttons here, trusted buttons, right? Which are just one wire GPIO. But anyway, I did a whole presentation about how to get around trusted buttons. And then this is the interface. Okay, so now this computer, this hardware thing, what does it do? Well, it has code to do a screen. It has, user input. It has, message parsing, right? It's got, you can't see this, message parsing. It has all of this stuff. And typically these interfaces suck, okay? Right? It's a very, very, the current hardware has very, very limited, they're like embedded systems, right? So they're very limited user interfaces. But what did I just describe, right? So what did I say these things have to have? They have a display, they have user input, right? They do have some sort of message parsing. Maybe if I draw another kind of device over here, it will perhaps look something. It's not the BitFi. Okay. BitFi. Okay, right. It's basically, it starts to sound like a smartphone is what I'm trying to, not the BitFi. Okay. It starts to sound like a smartphone. Now, because no one likes to go back and learn their history, there is a computer science researcher that he was pre-Twitter, so no one modern actually knows about him. But they did discuss this kind of problem. So Peter Gutman, in his thesis, which I'll show over here, he talked about this problem. And in this problem, he says you've got levels of protection designed by crypto hardware. So the first level of protection is like the minimum amount of protection. It just has the private key, right? This is the simplest crypto hardware. Private key is over there, and this is what it does, right? So this is like this is like the 608 level of protection. It's got the private key, and that's it, right? Level 2 is we add some sort of session key on top of that. So you can't just go ask the private key to be a signing oracle. You have to have a session key that is somehow protecting that session to access the private key. Okay, level 3, there is some sort of metadata, right? So now there's more information about the key, what key to use. It starts to get a little more complicated. Level 4 is your crypto hardware has some sort of command verification to make sure that it's parsing a command and everything. And then level 5 of a protection is a whole app level functionality. Okay, so, but there's a problem. Okay, and the problem is that as you move up, okay, as you so he's talking about the different levels, and then he talks about can we move the functionality to an even higher level, tier 5, given the coprocessor even more control over the message handling, right? So although it's possible to do this, it isn't a good idea, since at this level the coprocessor will potentially need to run message viewers to display messages, editors to create modified messages. Okay, well, so the cryptocurrency hardware doesn't do editors, nor does it handle mail, but it does do TOTP. There are apps that people are adding to this cryptocurrency hardware. There's lots of other stuff that's being added to the hardware wallets. Here in the 90s, the rage was mail apps. So he talks about mail software and a whole host of other applications. And of course, these programs will need to be able to handle MIME attachments, HTML, JavaScript, ActiveX, and so on in order to function as required. In addition, the coprocessor will now require its own input mechanism, a keyboard, output mechanism, a monitor, mass storage, i.e. maybe flash storage, right? And other extras. At this point, the coprocessor has evolved into a second computer attached to the original one. And since it's running a range of untrusted and potentially dangerous code, we need to think about moving the crypto functionality into a coprocessor for safety. Lather, rinse, repeat. The best level of functionality, therefore, is to move all crypto and security-related processing into the coprocessor, but leave everything else on the host. Right? So that is the issue with cryptocurrency hardware, right? So you almost cannot. It's kind of we're in this tough situation where you cannot move. On one hand, we can't have just the key, because if it's just the key, then people are assuming, oh, your laptop is going to be compromised. Oh my god, it'll be able to sign. But then we've moved everything in to the cryptocurrency hardware wallets, where now this thing is its own computer, running all this code, doing all these other apps, being a password manager. And now we need a crypto coprocessor for the crypto coprocessor. So this is the state of cryptocurrency hardware wallet. It frankly sucks. I am not a fan of really any of the cryptocurrency of the hardware solutions because of this problem. Like, right, there is not. It's a challenging problem where they have not found what exactly has to be controlled, and I mean, but you can't come at it. So on one hand, you can't come at it with the let's just put the key there, but the other hand, I don't know. We're not doing anybody any favors by moving the whole application in there. So that's all I have. A little history lesson from Peter Gutmann on how to do cryptographic coprocessor design, which he's been talking about for like at least 30 years. And I would highly recommend you check out his stuff. But that's some of the discussions I've been having within the last month, and I just wanted to make this video so now I can just point people to the video.